Here we're going to talk about indeterminate forms and L'Hopital's rule. In an earlier section, we found that the limit as x approaches 0 of sine of x over x by using tables, since we could not use direct substitution. In this section, we will learn a new way to take this limit and others like it. So this is L'Hopital's rule. It says, suppose f and g are differentiable functions and g prime of x is not equal to 0 on an open interval that contains a except possibly at a. Suppose that the limit as x approaches a of f of x over g of x has an indeterminate form, which looks like 0 over 0 or infinity over infinity. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, given that that limit exists or is positive infinity or negative infinity. Let's see how we can put L'Hopital's rule to use. Alright, so for part A, we have the limit as x approaches 0 of sine of x over x. And if I were to use direct substitution, so I'm putting ds over my equal sign to represent direct substitution, I would get sine of 0, which is 0, over 0. Now this is one of the indeterminate forms that we had discussed earlier. So because this is an indeterminate form, we are able to use L'Hopital's rule. So I'm going to go ahead and put an LH over my equal sign to denote that I am starting to use L'Hopital's rule by taking the derivative of both my numerator and my denominator separately. So the derivative of sine of x, we know, is cosine of x, and the derivative of x is 1. So now I can go ahead and I can use direct substitution because I no longer have division by 0 when I use direct substitution. And I know that cosine of 0 is equal to 1. And so finally, my limit is equal to 1. All right, let's look at part B now. Part B says we are taking the limit as t approaches 1 of t to the 8th power minus 1 over t to the 5th power minus 1. Now, notice that if we used direct substitution, we would get 0 over 0. So at this stage, we want to identify which indeterminate form we have, just so that we can make sure we can use L'Hopital's rule. So over here, I'm going to identify that this one has the indeterminate form 0 over 0. So now that we've identified that, I'm going to go ahead and use L'Hopital's rule. And we get the derivative of the numerator is 8t to the 7th power, and the derivative of the denominator is 5t to the 4th power. And notice that we can use direct substitution now. I also could have divided out some of those t's so that there was no more t's in the denominator. But if I simplify that, we end up getting 8/5. And for part C, if I took the limit as x approaches infinity of the natural log of x over x squared, that's going to go off to infinity over infinity. So that's one of my indeterminate forms, which tells me that I can once again use L'Hopital's rule. All right, so if I take the derivative of the numerator, I'm going to get 1 over x, and the derivative of the denominator is 2 over x. And I'm going to write that as 2 over x over 1, so that I know I can multiply by the reciprocal. So if we simplify that, we end up getting the limit as x approaches infinity of 1 over 2x squared. And as the denominator gets really, really large, the numerator is a constant, and so it's not changing, and so what happens is that fraction goes off to 0, and that is our final answer for part C. In example 2, we want to find the following limits, and for all of these, again, we want to check that they fit one of our indeterminate forms. So part A, we have the limit as x approaches 0 of x minus sine of x over x minus tangent of x. And if I were to plug in 0, I would end up getting 0 over 0. So that's one of our indeterminate forms. So we can go ahead and continue on by using L'Hopital's rule. Okay, so the derivative of the numerator is 1 minus cosine of x, and then the derivative of my denominator is 1 minus secant squared x. And one thing that we could do is, because right now, if I evaluated secant squared x and I plugged in 0, that's going to give us 1, and that would mean our denominator would be 1 minus 1, which is equal to 0, and we don't want that. However, hopefully you remember from trig that we have one of our Pythagorean identities, and it turns out 1 minus secant squared x is equivalent to negative tangent squared x. And from here, if we plugged in 0 again, we would still have 0 over 0 in our both our numerator and our denominator. So it turns out that we're going to have to use L'Hopital's rule again. And when we do that, the derivative of our numerator, 1 is a constant, so that's 0. And then the derivative of negative cosine ends up being sine of x. And then for negative tangent squared x, I'm going to use the power rule and bring down the 2. And then I still need to use chain rule, so I'm going to multiply by the derivative of tangent, which is secant squared x. So from here, I want to use some trig identities that will help us so that we don't get 0 over 0, because right now, if I plugged in 0 for x, sine of 0 is 0, and tangent of 0 is 0, so we would still get the indeterminate form. So let's see if we can use some trig identities. First off, I'm going to pull out the negative 1/2, and then I'm going to have times sine of x. That's from my numerator. And the reciprocal, or if I brought tangent to the numerator, that would turn it into cotangent of x, and cotangent is the same thing as cosine of x over sine of x. And then secant squared x, if I wanted to bring that to the numerator, that's the same thing as cosine squared x. And so what's going to happen is this sine of x and this sine of x will divide out, and we have the limit as x approaches 0 of negative 1/2 times cosine cubed x. And now I can go ahead and use direct substitution, because I'm no longer going to have one of my indeterminate forms. And I know that cosine of 0 is 1, and so my final answer for this limit will be negative 1/2. All right, let's move on to part B, which says the limit as x approaches 0 from the right-hand side of arctangent of 2x over the natural log of x. And if I plugged in 0 for both of these, if I used direct substitution, I would get the indeterminate form 0 over 0. And notice that we're approaching from the right because the domain of natural log of x is 0 to infinity. So we can't plug in negative numbers. That's why we're taking the limit as x approaches 0 from the right-hand side. So because we have the indeterminate form 0 over 0, I can go ahead and use L'Hopital's rule. Okay, so the derivative of arctangent of 2x is 1 over 1 plus the quantity 2x squared. And then I need to use chain rule, so I'm going to go ahead and multiply by the derivative of the inner function. So that's going to be 2. And then the derivative of natural log of x is 1 over x. And so if we do some algebraic maneuvering, I'm going to rewrite my numerator as 2 over 1 plus 4x squared, and then I can multiply by x over 1. And I'm going to use direct substitution now, so I have 2 times 0 over 1 plus 4 times 0 squared, and that's going to simplify to 0 over 1, or just 0 for that question. Okay, now we're on to part C. If I take that limit, which is the limit as x approaches 0 of e to the x minus e to the negative x minus 2x all over x minus sine of x, I'm going to end up getting the indeterminate form 0 over 0. So again, I can use L'Hopital's rule. So instead of rewriting that limit, I'm just going to move over here, and I'm going to use L'Hopital's rule to rewrite that as the limit as x approaches 0 of the derivative of e to the x is e to the x, and then minus e to the negative x, that's derivative is e to the negative x times negative 1, so that's going to change into a plus sign. Minus 2 over 1 minus cosine of x. Now, if I used direct substitution, I would end up getting 0 over 0 again. So e to the 0 is 1, and there's 2 of them, so it'd be 2 minus 2 over 1 minus cosine of 0 is 1. So that's going to be 0 over 0. So let's go back, and we're going to use L'Hopital's rule again. So I have the limit as x approaches 0 of e to the x minus e to the negative x. The derivative of minus 2 or negative 2 is 0, so I don't have anything there. And then the derivative of 1, that's a constant, so that's going to be 0. And then the derivative of negative cosine, that is going to be sine. Let's see if we can use direct substitution now. So that would give me e to the 0 minus e to the 0 over sine of 0. And that would be 1 minus 1 over 0. And once again, we'd have 0 over 0. So let's see if using L'Hopital's rule again will help us. So the derivative of e to the x is e to the x, and then I'm going to have plus e to the negative x over cosine of x. And that's going to equal, if we use direct substitution now, e to the 0 plus e to the 0 over cosine of 0. And e to the 0 plus e to the 0 is 2, and cosine of 0 is 1. And finally, we get that our limit is 2.